So, yesterday I made a short introduction to what is called the birational Anabelian Grothendieck birational Anabelian geometry. And what is the main point of that? So, this is really a big point. So, Grothendieck's birational, because I said I speak only birational, therefore, birational Anabelian geometry. So the main point is the presence of a strong arithmetical action. And therefore, the Anabelian curves should be curves over finitely generated fields, and the Anabelian one-dimensional objects should be finitely generated fields, and so on and so forth. And so I did not say much about Anabelian phenomena, but I said that in general, Anabelian phenomena, we call Anabelian phenomena facts which deduce about arithmetic and geometry from pure Galois theoretical aspects of the situation. And it was maybe one of my big surprises to learn from Bailey, who was visiting Heidelberg when I was writing my second thesis, the habilitation thesis, the following. So this was in the ICM 1990 Kyoto, and that was in a satellite conference. And what appeared further in the proceedings of this, editors Fujiki et al. And so this is somehow the precise source where you can find this written down, but I learned from Bailey that actually Bogomolov makes the following claim. So let be K any algebraically closed field, and consider, maybe before that, L fixed prime number K algebraically closed field, and K over little k function field, transcendence degree, maybe I will say, I'll introduce this notation now, transcendence degree bigger than 1. And then you denote by K dashed the maximal abelian, well, K dashed over K. Maximal abelian pro L extension. What does it mean? This means that K is K adjoint L infinity. You take all the roots from all possible elements of K, yes, L infinity. And then K double dashed over K. Now, sorry, I use the same notation in my section conjecture talk, but there are not so many possibilities you can play around with notations, therefore. So this should be now the maximal, and now it's really over K. The maximal abelian bicentral. Bicentral pro L extension of K. So what does it mean? So this means that actually, okay, so and I will write then further. Now Galois over K, Galois K dashed over K. This is the canonical projection. Maybe let's give it a name for K. Canonical projection. How is the interpretation of this? Well, the interpretation of this is that the kernel of this is so this is surjective. The kernel of this is central in the Galois group, and it is this extension or this quotient of the absolute Galois group is the maximal possible quotient with this property. Okay, and now Bogomolov's claim was the following. Thank you. Yes. And different from L. This is very essential. Okay, and now Bogomolov's claim. Or maybe, yeah. Claim. Bogomolov. Lokchit. Is that the field can be recovered, actually this is maybe the right, reconstructed from this relatively small quotient of the absolute Galois group, because this is really a very small quotient. So maybe I should say here, remark, yeah. What is the Galois group here? So the Galois group here, G k dashed over k, this is simply isomorphic to ZL mod k. Yeah. As an abstract group, this is a free pro-L abelian group. And now, what is this group? Well, this is a very serious, big question because of this assertion. Yeah. Actually, this is a free group, pro-L free group. You can't expect to get any information about the cardinality of K, where this says, I see things you don't imagine and don't. Yeah. Okay, so maybe this, I call this a claim actually.
So the statement was that the kernel of this projection is central?
Yes. Yeah, so this is, you take the absolute Galois group and then you consider the L infinity descending central series, and this is simply the first quotient, this is the second quotient in that. And then you can actually, so if you know this, the projection is encoding in this because this is simply the quotient of this by its commutator. Yeah. And now
this doesn't work for curves?
I will say everything, yeah.
The transcendence degree
has to be 2, yes. So the point is maybe I will make remarks at the end. Fine. So what can I say about this? So I have. It's difficult for me to say too much about this because actually Bogomolov announces at theorems, and if you look at his paper, then everything is a theorem. But unfortunately, this is actually by all the standards, this is still a claim. Okay. So what is the status of the art with this? Maybe. Yes. So the first point is in general. What means in general? It is for general K, this is completely open. And for K algebraic closures of finite fields, okay. That means for, and I will say more than just that you can recover the field. Before that, let me make a definition. So definition, let K over K and L over L be as above. Oh, sorry. This is a problem because this L, but so I'm writing in tech, yes? This is a different L than that. So then maybe I can, yeah. Oh. Okay.
We will understand.
Yeah, be as above, be function field over algebraically closed fields. Then an isomorphism phi dash defined on is called liftable if can be lifted to an isomorphism so very easy definition. Yes. Then the theorem I want to convince you is true is the following. Our theorem. So, in the above notations, suppose transcendence degree of k over little k is bigger than 1 and little k is algebraic closure of finite fields, some finite field. Okay, then the first assertion is there exists a group theoretical recipe which recovers the function field, so k over k from and the second, this recipe is functorial in the following sense. So the recipe is functorial in the following sense. So given, so for every L over L, L over L. You're right, thank you. Well, that is the perfect closure. Well, I would say it recovers up to pure inseparable extensions. So for every L over Kel function field with little l algebraically closed, there is a canonical bijection from here. You have liftable isomorphisms phi dashed defined on g k dashed over k, that is g l dashed over l. And now this is not obvious, but it's a nice exercise. If you have a liftable isomorphism and you multiply with an L-adic unit, what you get is again a liftable morphism. That means you have to factor to mod out the L-adic units. And here, isomorphisms of function fields I defined on k over little k, L over L. So that means isomorphism of function field means this maps. And I have to put here pure inseparable cover. And now these are not function fields, but it's clear what I mean. Yes, pure inseparable closure of the function field, and up to Frobenius. Yeah. Okay. Fine. So this is the theorem one can prove, and I will make more remarks to answer several questions. So the first and maybe more important essential remark is that a similar result was proved by Bogomolov-Chinkel for transcendence degree of k over little k equals 2. And now I say similar. To be honest, I don't know what is the precise status of the art because I've seen so many variants of their paper. The first one was they considered only the case when X had models whose fundamental group was finite, and so on. Okay. And I do not know whether this form was proved or only they show that you can recover the field and so on and so forth. So two.
And the theorem is for greater than 1.
This is, they prove it for transcendence degree equals 2. I asked it to be bigger than 1. 2 is bigger than 1.
The special case.
It's a special case.
This is okay. This was proved before that.
Yeah. So it's difficult to say when it was proved. Because the main ideas for the proof of this started in 99, and I discussed with everybody, and they asked me many times, email and discussion and so on. I explain all the time my ideas, and I think that
Now, in Bogomolov-Chinkel, they use a little the structures. They use a little knowledge of when
well,
theorem and
I will do the same. 2. Now your question, please.
So also in the claim, is it also necessary to say that only the inseparable closure can be recovered?
Yeah. So everywhere it's up to pure inseparable cover. Yeah, because the Galois theory does not see up to pure inseparable extensions. Okay. Thank you. If I forget to say that at some place, it should be said. Yeah. Now, 2, this answers Mignon's question. So, transcendence degree k over little k bigger than 1 is necessary because there is a theorem, a famous theorem by David Tarbeter and myself, because Beta Pop proved the following: if transcendence degree of k over little k is 1 under the little k algebraically closed, then gk already the absolute Galois group, yeah, so out k over k is profinite free on little k many generators. That means this is the only information you get from the full Galois group, therefore also from small quotients. You can't expect to get anything exciting. Okay, now let's go on with the remarks. Third, so by taking limits, whatever that means, and the theorem implies pro L, respectively full Galois versions of Bogomolov's claim.
Clearly, free, you don't have to worry about P.
No. Actually, it was a little bit of a surprise because everybody you would ask, all the experts say, no, it has to be something, it has to do something with P. But it does not have to do anything with P. Yeah? So this is, well, the so-called geometric Shafarevich conjecture. Shafarevich conjecture says in general, so if you have K global, then let's introduce another notation, maybe F global field. Then the kernel of the cyclotomic character in GK is profinite free. Now, when you have a global field, the constants are finite field, therefore the kernel of the cyclotomic character is what? Is exactly the Galois group of F little k, where k is algebraic closure. And this is a proof of the Shafarevich conjecture. And we do not know the answer in the arithmetic case, yeah, in spite of a few wrong proofs given from time to time.
How is this property related with cohomological union?
Yes, the point is, so naturally profinite free means also chronological dimension 1. That was known maybe by, yeah, general stuff, Serre. And maybe Serre also knew it. It put it there because it was known. Like in Euler times, many things were known. He just put it in books. Put them in books, yeah. Okay. And fine. And now, by taking limits, the theorem implies a pro-L version, maybe a full Galois version of the claim, of Bogomolov's claim. Well, of the assertion, I will say, yeah. And then 4. Now, what is the relation with Grothendieck's Anabelian geometry? If you give me a finitely generated field or a finite field, then I can enlarge the constants to the Galois to make them algebraically closed. And then I'm left with a geometric absolute Galois group. And this assertion tells you that if the transcendence degree is bigger than 1, you can recover everything from this part. And because everything is functorial in this way, you see that actually I can recover also the assertions in the arithmetic form. So the theorem implies I will say, pro-L geometrically abelian by central. So only the geometric part should be abelian by central pro-L version of by Grothendieck's birational Anabelian conjecture. Well, but goes far beyond it, yeah. Okay. And maybe 5, there is though something which you would like to know concerning Grothendieck's variant. You would like to have a full pro-L. What is going on here? You do it only geometrically abelian by central pro-L, or maybe geometrically pro-L. Now, what if you do not enlarge the constants to the algebraic closure? It seems that the conjecture of Grothendieck should hold, and also should hold in the pro-home form, and so on. So, nevertheless, the pro-L form of the arithmetic birational conjecture, birational NF conjecture, is open. We were thinking yesterday with Mohamed and Scott Corey about what one could do, maybe over the p-adics and so on. Fine. Now, these are the remarks, and what I plan to do is to give some hints about how the proof goes. Yeah? And maybe strategy of proof. Here somehow about my personal experience with this. Actually, at the beginning I was a non-believer, but eventually when a few things came together, I realized, so that could be actually, something could work.
Can I ask what is?
Please.
Do you ever state the birational view?
Actually, you're right, I did not. But that means that is exactly the same assertion about finitely generated fields. You just take, now not Lifter, you simply take isomorphism of the absolute Galois groups, and then you take isomorphism functions with modulo Frobenius. And that is the conjecture.
Modulo anything.
Modulo anything, because also here, these these isomorphisms lift only to the second central term. If you want to lift them further, it does not work. And so that at the billion level, you don't have to factor anything out. You are only left here. You always have to factor Frobenius out because Frobenius is not seen by Galois theory.
And I guess you have to formulate how to have up to inner conjugation, or that it's an isomorphism of the algebraic global.
Yeah, so actually this has, thank you, so yeah, this you can reformulate it also in terms of isomorphisms of the algebraic closures modulo isomorphisms of the algebraic closure over the base field and so on. But I don't want to. Okay, so maybe.
So in this case, one gets a candidate isomorphism, but one cannot prove that it's the one started, that it gives back the isomorphism of the other one.
Well, and then that is the problem, that actually you have to transform it in such a way that finally it gives you the isomorphism started. Yeah.
Maybe you don't want to do it. Could I ask you to write down?
Yes. Okay. So then the assertion is the following. So. Okay, so L, K finitely generated fields, K infinite. Yeah, then, so 1, there exists a group theoretical recipe to recover K as a field, yes? From, well, again, up to pure inseparable cover, yeah? So from the absolute Galois group. And second, there exists a canonical bijection between, I have here isomorphisms, phi defined on G, K values in GL. Well, up to inner. Yeah, so, okay, that means outer isomorphisms and field isomorphisms. Phi defined on K, well, Li, Ki, modulo Frobenius. Okay. So you see that it's exactly as this, just that actually you have here this freedom that you can multiply by units and you still get liftable things. But the point is, as I said here, because of the much, so to get such an automorphism, you kill all such freedom you had before, and what you are left with are inner automorphisms only. Yeah.
So in this form, do you impose something on the base field?
No, I don't say anything. Just that actually this is infinite. Yeah.
Can one recover which coefficient of Galois, the Galois
yes. Yeah, part of this is naturally you recover all this. And actually you can put here open automorphism, and then here are embeddings with finite degree and so on. So you can do more. And in positive characteristic, this is more. You can take open homomorphisms here and then embeddings of fields. This is Mochizuki's theorem, which Scott spoke about yesterday. And then one has also geometrically pro-L variant of this, and so on. In positive characteristic, it's completely open whether you can do something with a home form. We expect maybe that one can, and one has conditional forms of it, and so, and maybe this theorem I said here, theorem, actually what I will prove is not this, but exactly what you were asking before. What I will prove is you reformulate, you put some extra information on this Galois group, which is on this abelian group, which has to do with the decomposition structure, and but it has to do with the decomposition trees or graphs of the function field, and from that you recover the information. And then this takes a home form. Then you simply have a home form of this, but it's not clear how to recover that extra information you need in that form of the theorem from this. Okay. Fine. So now I come to a strategy of proof.
In your remark 5, you mean open is in positive characteristic.
Yes, in positive, but I think that, well, in positive characteristic case, and I think also in characteristic 0, we don't have a pro-L form. We have,
In the yesterday's talk.
but this was geometrically pro-P.
Arithmetic means.
Yeah, I mean, you should. The point is, when you allow an algebraically closed field as a base, after that you can distinguish points. For instance, suppose that you have a curve. If you can enlarge the constant to the algebraic closure, then you see the distinct points of the curve. But if you work pro-L, you see only bunches of points together. And now it's not clear at all how to do with those. So the prime divisors have degree 1, but in pro-L, prime divisors do not have degree 1. And for instance, the problem, how do you read off the degree of a divisor, of a prime divisor? All these things are not clear. Okay, now let me tell you the strategy of proof. So I will start. Actually, this is very similar with Scott Corey's talk from yesterday. So remember Kuma theory. Well, and actually that common result of ours was inspired by this development. Remember Kuma theory. So you have this. So maybe let's say first n should be always with e some power of L. Then what says Kuma theory? You have k times modulo n, where if I have an abelian group, this means the quotient by the nth. So this is by Kuma theory, this is isomorphic to h1, okay, k and mu n. But now there is no Galois action, and this is maybe not canonically, but anyhow isomorphic to simply hom and z mod n. Yeah. And now taking limits, oh, the technology. What can I do? Fine. Now taking limits, you get k hat, so which is by definition the L-adic completion of this, so k times L to the e for all e. Then this is isomorphic to h1. I don't have to write continuous because it's clear that I mean. Yeah, which is isomorphic then to hom. Now this cont, yeah, continuous homomorphism. Okay, and you definitely know this as an abstract group. That means you know this as an abstract group. And now remember that here embeds k times modulo k via the completion map. And when you see this, you see, now I know what I have to do. Maybe I have to recover this group as an abstract group, and I have to interpret this. So now, interpret, so recover when I say recover, it's clear I have to recover this from my graph. So from this. and then interpret as projectivization. I prefer this instead of Scott Corey's notation yesterday. With I don't know. Is this the canonical notation projectivization of a vector space? If it is, then I use this. If not, I use.
Which is which?
So this is my question. So if I have a projective space over a field, what is the canonical, the usual notation for the projectivization of the vector space? Is this?
So what is projectivization? What is the
Ah,
hyperplanet
so
infinity?
this is by definition V
One-dimensional curve.
without 0 modulo K. I say that this is also terrible. So Scott, this is so this is the projectivization of K plus, yes. And then, yeah, as the projectivization of this infinite dimensional space, and then recover in this the lines, yeah, the so-called collineations, or which is the same as the lines. So we must be able to say where the 3 points are, and then use the fundamental theorem of projective geometries, and I think Scott mentioned this yesterday, so this is maybe Athens geometric algebra. And show that the field now, this, as a K vector space, that means as a K algebra, can be recovered. Okay, and then finally, the final step is, okay, so I don't have to make any step. And maybe in the functoriality, so then in the functoriality, okay, so now show that the recipe is functorial as indicated at 2, is compatible with liftable isms, in particular, and Galois theory. So this is the strategy, and actually, so as I said, so this was maybe my idea from actually 1999 in, and maybe many details were worked out in 2002, and I visited the Institute for Advanced Study. And so then a final paper where everything was put together was in 2003, and it appeared on, I think it's in the archive, something, you can Google it, yeah. Nevertheless, here was the Galois theory, so the local theory here, I will say more about local theory is full pro L. Yeah, because to be honest, I did not know how to do it then in this form. Because there are several places where you use an inductive construction, but what happens when you work in this setting, namely abelian bicentral, if you take a subgroup, an open subgroup of this, you do not have for that open subgroup its abelian bicentral. If you take an open subgroup of this, take the preimage in the absolute Galois group, and now for that preimage, which is an open subgroup of the absolute Galois group, you do not have this quotient. Where if you work pro L, then you have the quotient, and you can do things by induction. And this is one of the reasons also why, as I remember, why that was also a technical problem Bogomolov and Chinkel had to deal with, and then, well, supposedly they could not solve it, and therefore when you want to go to do something for dimension 3, then normally you want to do induction, but induction does not work. And this is actually this.
But if you want to do Pro-L, you have more difficulty for proving interminjectivity. That everything, every isomorphism come from, not only define something, but come from something.
No, I think that will work. I think that if you work Pro-L, then you can go up. So, as I said, this disappears.
You do it
only.
for all.
Yeah, you do it for all, and then at every stage you have it, and then, yeah. It's not. Please.
Why is it the same to show that you recover it as a k-vector space or as a k-alpha?
So it comes from the. You see that actually what you get is. It's not. I don't see that it's the same.
So it's not IE.
What?
And
Yeah, and. Thank you. That's very good. Nothing is so. You simply work out the details and you say, this is actually okay algebra. Yeah. Okay, so now this is the plan. This is the plan for what we want, we have to do. And maybe before I plunge into technical details and so on, I should say that this strategy at least is similar to the strategy to solve this problem. Nevertheless, here you have less difficulties of the following nature. If you look at peak of varieties, because everything is over field of finite type and so on, those are finitely generated. And in particular, you can kill a peak by simply inverting, replacing the variety by an open, Zariski open subset. Yeah, can do such things. And after that, you do not have to do, you see, the divisors become, actually the divisor group is virtually the same as the principal divisors and things like this. Now, in the algebraic, in this setting, you can't expect such things to happen. And this is also related to the, what I said here, I do not know precisely in which form now it is proved. In the initial paper by Bogomolov and Chinkel, they looked only at fields K which have models whose peak is finite. Because of the same reason, then the principal divisors are virtually the group of the divisors. And then you are in business, yeah? Now, why? This guy is the group of principal divisors on any projective nice model, yeah? And virtually then you have this somehow. Now I have to say that actually this is the biggest and the most difficult battle you have to fight to recover this. And also in the original paper by Bogomolov, where he made this claim, he somehow says that virtually obvious how to recover this. Until now, I don't see any obvious way to recover this. And I said, this is, pardon?
Recover that inclusion?
No, to recover this inclusion, if you want. In particular, to recover this group, yeah, so this is really something. And it turns out that, so in my strategy, you recover it at the very end when you know very many things. Okay, now maybe just as a warm-up for this, so how to do this? So let's say that, so consider x over k projective normal and so on, nice model of the function field. Now, so what means model? So it's a variety, it's an identification of the function field with this function field. Yeah? Okay, and then you have an exact sequence of the following form. So these are the principal divisors. Maybe I will say V in dx, where these are the prime veil divisors.
I'm sorry, what are those dot dot dots?
Maybe further properties like smooth and so on. We do not know this in general, you have, but projective normal, well, let's say nice. Yeah. So model of k, and then here is peak of x. Yeah.
Speaking
Maybe
of
I don't want to
the
say this.
parameters,
Sorry, I don't. I want to say only the divisor classes. Okay. Better. Yeah. And now this is somehow, this was a picture which one uses here, as I said, because so think that this is a function field or a finitely generated field. Then this is a finitely generated group, and in particular by inverting finitely many divisors, which are generators, you kill this and then you virtually get some units, group of units here, because now you do not work. So here the global sections are only K, the multiplicative group. But in general, then you have some global sections, then this, and knowing the divisor group, you virtually know this group. And then you are in business. Very easy, yeah? And all the work starts after that. But in this situation now, you don't have, well, if K is algebraically closed, then this guy can be very big. And now if you take LA completions, that means you tensor with Z mod L and so on, what you get finally is the following sex sequence. Here is the Tate L module of the class group of X. And then here is the eddy completion. And then here are the, but now you have to complete it, this pro L, L-edically, not pro L. So, and then you have ZL, V. And then here you have the L-edically completed X. Okay, now what do you intend to? You want to have this group from somewhere. And if you look at this picture, you know this because of this. And if you know this, then you say, okay, if I know these two guys, then I know also this group and this group. And eventually, so now you are close, you are in an environment where you hope to say something about this. And actually what you really, so then, what you really do is, what you really can do is the following first approximation of, so get first approximation of this, which is, and this is indeed what you really can get. Now inside here, it turns out that you can discover this group, Z localized. So now these are the rational L-edic numbers, yes, V. Turns out that you can discover this group inside you can reconstruct this group, and then you simply take the pre-image in here, yes, and I call that maybe LK, yeah, it's the pre-image. And naturally, you can't do anything about a kernel. This kernel is here. But this is also known. Now you see. So, which is LK by definition. So, this is div, the pre-image of the, yeah, which I call the divisorial lattice inside K hat. And now some observations. The point is, it's surprising, but this guy is a birational invariant, because it turns out that if you're, I said, maybe nice should be maybe sufficiently rich. Yeah. If your model is sufficiently rich that if you start with some projective model, then there is a recipe by which you can say what you have to do in order to make it sufficiently rich, then what you get is big enough. Yeah. Then this is becomes a birational invariant, And I can tell you what it is. Suppose that your model is projective and smooth, then this is nothing but the L-adic dual of pi 1 of x. Well, the L-adic dual of the, so of pi 1 ab L. Which we know that actually this pi 1 of x is a birational invariant for projective smooth, well, for complete smooth varieties. And this, what is here in the case, you have models which are smooth, complete and smooth, is exactly that, which is a birational invariant. And then you see that actually this is a birational invariant, although you think that actually depends on x. Well, the pre-image, this depends on x, but the pre-image does not depend on x. And that is the first approximation of this group, which I call a divisorial lattice. Okay.
How do you handle that you don't have a roof?
So this is, so actually at the beginning these were big problems, and I had discussions with Samueli, who was supposed to give a talk in the Bourbaki seminar about this, when these were very incipient, so he gave a talk about the arithmetic case. And then he came, whatever assertions I made, he came and said, no, this is not true, because look, And eventually I realized you do not write pick here, but you write the class group. And actually everything so if you really try to use theorems from geometry, you will get very big troubles all the time, because after that you have to enlarge x, or maybe to shrink x, and so on. And eventually I realized that this here has a complete birational interpretation. And what you work with is that only. And the birational interpretation of this coincides with the geometric picture when x is smooth projective, for instance. And now how do you reduce to that? Mainly you need only finiteness assertions. And you use de Jong's alteration theory, and there you know that everything is as you expect, but well, that happens after finite extension, so finiteness theorems hold in the same form after that. Yeah. But as I said, so that was for me also a learning exercise to realize that now you forget as much as you can about geometry, because all kinds of pathological cases. Would have to deal with all kinds of pathological cases, but what I need were only finiteness assertions, and those you could finally formulate in a birational way. Okay, now what is the plan then? Hence, plan. You would like to have what? You would like to have for projective, maybe for projective or quasi-projective models, you would like to have all the set of all the prime divisors. And for that, now that is, we'll come to that later, but so the first step is, so one, recover the prime divisors of k over little k. Now what are the prime divisors? So these are, so I remember now the picture from yesterday. So you denote xk should be the projective limit over xi, with xi over little k projective, maybe not, so normal projective model of k over little k. And then you remember that this has the interpretation as, so this is actually a point here is a valuation, and that valuation corresponds to a sequence of points xi on every I. What was the correspondence? You simply take, well, yesterday I made this assertion in the arithmetic situation. I make it in the geometric situation, but it's exactly the same. So, and how does it work? So if you have V, then you look at xi, which should be the center of V on xi. And if you have the points xi, then you get V by simply saying that the valuation ring is the union of all the local rings which dominate each other, and so on. And now what is a definition? What is so V in X V is called prime divisor if it satisfies the following, the equivalent conditions. So this is an exercise that these are indeed equivalent. So there exists, and first V is non-trivial, and the transcendence degree of the residue field over K is transcendence degree of the big field over K minus 1. And that is equivalent to, there exists I such that xi has codimension 1. Yeah, and then that's equivalent also to maybe V is discrete valuation with the residue field like there. So, but already from this it follows that V is discrete and so on. Yes. So these are the prime divisors of K. And now, after that, you want to recover the geometric sets of prime divisors. So two. Now, well, maybe before the geometric sets, I would say recover the birational Parshin chains of K. And now what is a birational Parshin chain? I said already yesterday, but I repeat once again. So Parshin chain, what? Birational. Parshin chain. Well, it's a sequence of evaluations, so V, it's a sequence of evaluations V1, V2, and so on, Vd, where D equals transcendence degree of K over K, maybe VR, with R less than D transcendence degree. Well, what is this? So V1 is prime divisor of K over K, then V2 is prime divisor of the residue field, maybe of K1, which is by definition K over K, and then this is of K2, which is by definition KV1 over K, and so on. And now you have to stop after exactly at most. You can do this as most D times. What is this now geometrically? So you have here your variety here, X, and then you have, so this would be V1, and then now you have a line here. This is V2, and you have a point here that would be V3. Yes, and when you compose them, so yeah, so setting V equals VR composed V1, get a valuation on K with values in Z to the R, is ordered lexicographically. And what is the residue field? Well, the residue field is a function field, and what is KV over K is function field transcendence degree over K equals D minus R. Yeah, therefore you can go only R steps.
I understand what this means, but I am not used to the language for valuation. So what's the formal definition of composition?
Aha, so the formal definition, so this is it, okay. So now we are very general, yes? You take a valuation V on K. Then you have OV, the valuation ring, the valuation ideal, and here is KV. Now take a valuation ring of this guy. Yeah, now take maybe W on KV. That means now you have OW in here. Yes. And you take the pre-image of this, and that will be, is by definition, you can check it's a valuation ring, and that is by definition this. Okay. It's an easy exercise to check that if you have a valuation subring here, the pre-image is in K, it's again a valuation ring, and so on. What is the residue field of this? Of this valuation, you will have aqua. So then you have, so this is introduction to valuation theory, but it's very good that you asked. So then you have the following. First of all, what is the residue field? The residue field of W composed V is the same as the residue field of W. Yes. And what about the valuation groups? Well, the valuation, there is a canonical exact sequence of the following form. W of, so the value group of this goes into the value group of the, and then value group of K goes to 0. And, okay. So this, it turns out that this is a convex subgroup of this. So, and actually, there is correspondence between, if you have an evaluation, then what is interesting about valuation rings is that their spectrum is linear, and every overring of valuation ring is a localization at a prime ideal of the spectrum, and so there is a canonical bijection between the spectrum, between all the convex subgroups of the value group, and all the so-called Kersening valuations whose valuation ring contains the given valuation. So this is the, okay, now, and so that means, please.
Oh, so it's composition in the sense of composing the associated places?
Yes, and this is exactly the composition if you would speak in terms of places, and you would compose places.
Places, the partially defined map.
Yes.
Star to the residue.
Yes, and then infinite to infinite. Yeah.
Usually.
Yes, this is exactly the composition of the places. Yeah. And now these have somehow a nice geometric interpretation. The geometric interpretation is here. Well, not really. So if you give me an x, then the Paschen chain maybe has nothing to do with your x. But after you blow up enough on the new x, on a much richer x, you see exactly this picture. The first valuation will be the closure of the center will be a Weil prime divisor, and in that now, if you blow up further, you can do in such a way that the center of the second one will be actually maybe not exactly. If you can desingularize, I think you must be able to desingularize in order to do this, or to regularize. The center of the next one will be.
But if you wanted to desingularize in the previous one, so you.
Yes, in the previous, yeah. But I mean, I was thinking of this still in the ambient variety. And actually, to do this, and indeed to have everywhere what you think is really equivalent to regularizing, locally at least. Yeah. Okay, but I'm already 5, so maybe, can I finish? Because I am already 4 minutes. So recover the birational Paschen chains. All the time when I recover, I mean, give me a group theoretical recipe by which I can say that these are the prime divisors of K, these are the Paschen chains, and then recover geometric sets of prime divisors. What means that? So what is a geometric set? So geometric set. Well, you give any x quasi-projective normal, and then I denote by dx the set of Weil prime divisors of x But naturally, so this is a set of prime divisors of K. Prime divisors of K. And those I call geometric sets. And the question is, can you recover the geometric sets? Now, here, it's important to think in the right way, namely, not one set, but all the sets. I mean, if somebody gives you a set, can you say, this comes from some variety? And the answer is yes, one can do that. And
say the definition yet. Which one is it?
So I call us, if I have a, so what is a geometric set? The geometric sets are the sets of the form dx, where x is a quasi-projective normal model, and then this is the set, the set of prime divisors are exactly those which are the veiled prime divisors of x. So the veiled prime divisors of x, because they are normal, can be interpreted as discrete valuations on the function field with some property.
Okay, so for each projective normal x, we have one geometric set.
Yes. And only those are called geometric sets. And the question is, can you recover those? And now you see that this guy from here maybe comes into being somehow. If you recover this, then you know this object, you know this object. But now inside those, you have to recover this group, which is really something very tricky. And I will explain this next time. And where does it come from? It comes from the fact that for curves, for complete curves, you really can recover this, that LK in, because of a miracle of the structure of the absolute Galois group. If you know the inertia, then, you know. And the rest is a tricky induction procedure.
When you say recover the geometric sets, you mean together with the maps between them?
You naturally, so you also know the maps between them, because it will be. That means if you have an x and you have another x, you are able to say whether there is a map from one x, well, at least a rational map from one.
This means just a fund is bigger than C also.
This means exactly, yeah. Only that the set is contained in other than.
Well, yeah, but you could, I mean, you have to recover the inclusion.
Yeah.
And can you really tell exactly which are geometric or only big enough? Because it's hard to know if something can be contracted or not.
So the point is, suppose that, so this will not tell you very much about x. Why? Because okay, let's say that you have a very rich variety with a set x. Okay. So let's suppose that some x, you know that some x is geometric. Then every cofinite subset is also geometric, because you take the finitely many, so you take them all, you take the closure of the finitely many things, you throw them away, you did not throw away any of the rest, and that is. So this does not tell you much about the geometry of x. This does not say literally anything about the geometry of x.
Oh, quasi-projective.
Quasi-projective, yeah.
Oh.
No. And you will never know whether something is projective. Therefore, I denoted something, even this object here, for rich x, or for big enough x's, turns out to be birational object. But even for those, you do not know whether those x are projective. You could still miss points which are not seen completely by functions. Then.
When you say recover what prime divisor mean, it includes recognizing the corresponding inertia group?
Yes, it includes recognizing the corresponding inertia group and the residue, the Galois group of the residue field.
By induction.
By induction. But no, that's the point, it's not by induction.
Okay.
It can't work by induction because of the reason I told you. The decomposition group is a subgroup of. Now in this guy, you cannot do anything because you do not know. I will explain this next time. So, but I say, okay. So what is the decomposition group? Looks like this. Here is GKV and the inertia. Okay. Now this is isomorphic to ZL. And at the abelian level, everything is perfect. So this guy turns out to be exactly G of over kappa V. Those one. Now, what would amount going by induction? Going by induction would be to do the same now for I. And then the point is, you do not know what to put here. And this is the whole picture. Here breaks down everything when you work abelian bicentral. Until now, I do not know what, I mean, you can put here something, yeah? But I do not know what is the relation of this guy with the rest of the world. And then therefore, the induction procedure breaks down and you have to think in a completely different way. This is why actually when you want to do it already for dimension 3, you are in a completely different world than in the case of surfaces. Yeah. Okay, I will explain that next time. Actually, all these I will give you recipes for all this in terms of so-called lifting pairs by commuting lifting pairs. Okay.
Any questions for now?
So if the questions are not used up already, please ask them.